Hey everybody, this is Larry. This is day 30th of the March Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's farm. Russian doll envelopes. I usually record these live, so if it's a little bit slow, just fast forward or skip ahead or whatever you need, or watch on a bigger speed. The other thing is, just want to point out that I'm wearing these glasses. They're not regular glasses. I could see without them. They're more blue light glasses so that I could sleep better at night in theory. And the reason why is because for some reason Leetcode always only show new problems at midnight PST, and I'm on EST, which is 3 hours later if you want to record that or whatever. Anyway, it's 3 a.m. So yeah. Anyway, today's problem is Russian doll envelopes. So you're given to the array of so I got a pop-up right now. Let me turn that. Okay. Okay. So you have a 2D envelopes width and height. If only both the width and the height is greater than. Okay. Can you Okay. Oh yeah, I was gonna ask, can you rotate an envelope? But without it, then that's fine. Return the maximum envelopes you can. Maximum number of envelopes can you Russian doll? That's a very awkward phrase, but okay. Has to be strictly greater than. Okay. N is 5,000. That's a little bit annoying because I think 5,000. So the short story is that this is longest increasing subsequence, which is n square. But so n square and 5,000 square is a little bit slow is what I'm thinking of. And then the question is, can you do better? I mean, so the thing with longest increasing subsequence is that there's an n log n algorithm based on binary searching on the longest length. But in this case, there are two dimensions, so I don't know if that generalizes. I think it does, to be honest, but because I feel like I've seen similar problems before, but I feel like I've just been really bad about it, at least with respect to rotation. Let's see. So I mean, I think there are things you can do with respect to keeping track of frontier stuff. And what I mean by frontier is just only the other envelopes that you have to consider, right? For example, in here 6-7, you would never have to consider 2-3 because 5-4 dominates it. So I think that's kind of a way to do it. But is it good? But that's I don't think that that's log n. Well, that's not gonna be n log n. And the tricky part is that for me, and I have to figure out how to prove this, or at least in my head, or at least be convinced about it, is that you can have, like, you know, someone like this, dot dot dot, and that'll be like the numbers you have to consider. And if your entry is like 101, 101, well, which one would you take, right? You can take all of these, but I don't know that you can greedily take only one of those, right? So I think that's the part of that that I'm trying to figure out in my mind a little bit. And certainly, I mean, there are definitely optimizations that you can do, assuming that this is the case, but I'm not convinced that those are like going to be fast enough. I don't know how tight this n square constraint is, because 5,000 square, if there are a lot of test cases, it's going to be too slow. But if there's one test case, it'll be fast enough, which is one of the problems with Leetcode sometimes in general, especially for the contests. All right, let's do the n square one. It's dynamic programming. Let's do it that way, and then if it times out, we'll try to optimize it. And maybe we could think about the properties. I think the tricky part is that 5,000 is on that cusp of maybe fast enough, but also maybe too slow because it's like 25 million. But the overhead is not that big in general. Normally, I would also I would go top down because I think the transition is much more clearer there. But for me, I'm going to do this bottoms up because we're already talking about pushing the envelopes with respect to performance. So yeah. So first of all, the first thing I'm going to do is sort the envelopes this way. Even though I know that it only sorts the width, but we know that then we only have to check the height because everything before that, the width is already good, right? Yeah, and you can maybe even play around with some maths on that, but maybe like that's more of an optimization, so we'll think about that later. I think you can, I mean yeah, let's do it the n square way first, and then we'll kind of think about it. It's kind of this is one problem that I've always been a little bit weaker at. So I don't know, because I don't know. So because I feel like this particular variation comes up actually. I don't know why it comes up enough times, but every time I just been ignoring it. So that is a little bit my thing, because I think there's one observation that I have to make. But yeah, let's start with this. Okay, so let's just say best is equal to basically and what is best, right? Let's define it really. Best sub I is equal to the best or the most, it is the most, right? The most envelopes you can fit ending in I, ending in envelopes I, right? So then now we can do, for index range of n, and then for and we start with 1 as the base case because you can always have one envelope because that's the envelope that you have, right? And then now we could start with last envelope index, say, in range of from 0 to index exclusive. So that means that, okay, now we ask ourselves, can we add envelope of index after envelope sub last envelope index, right? So that's the question, and the answer is this can be done if and only if envelopes of index is of 0 is greater than envelopes last sub envelope index sub 0, and the same thing but for the second index, because it has to be strictly greater than on both the width and the height, so we have to check both. But this way there is a sort of a DAG, right? Because you're always going from left to right, or from right to left, pointing forwards, because you never have to look at an envelope that's going the other way. That's why we sort. And why do we not have to look at an envelope the other way? Because we know that if it gets sorted later, that means that at least one of the two elements is equal to or equal to one of your elements, right? And therefore, because it has to be strictly greater than, you cannot consider it because that's just the definition. And if it's tied, then the other number is smaller or something like that, right? So that's basically the idea. And this makes it like a little bit easier to do. And of course, if you know this and if you're really tight about the whatever, this is actually n choose 2 instead of, n square. So which just makes it faster, is what I mean, right? In this case, then let's do it. Let's add index is decode to the max of best of index, which means we take the best of this, or we look at the last index and then we add 1, right? So basically we add this envelope to the last envelope. That's basically what this is saying. Yeah. And then now at the very end, we just have to return the best of the max, which means that we just return, you know, which envelope has the most envelopes that we could fit in at the end. And that's basically the n square longest increasing subsequence solution. I mean, this should be okay. Yeah. But the question is whether it is fast enough. So we'll see. And it might not, which would make me a little bit sad. But oh no. Yeah, well, wasn't sure. What is this n? So we'll never know. We'll never know. I mean, it is fast enough. It's just that sometimes they will give you that's what I was saying earlier, in that with one test case, we know it's going to be fast enough, but they may give you multiple test cases and you don't know how many test cases there are. So like it may time out as a result, even though with one test case, it's actually not that bad. And n is 4186. Yeah. So this is dynamic programming. And then the question is, can I reduce this to n log n, which apparently may be necessary, or I should change to another language, because I think in Java this is fast enough, to be honest. And sometimes if you see me during the contest, you know, you'll see that it is fast enough. Or like I switch to Java sometimes if I do the math and it looks okay. But yeah. But then, okay, so the key thing to know for the n log n one, which is a little bit tricky to, at least from, I don't know, at least for me, a little bit tricky to kind of explain. But the idea is that, okay, actually, no, this one, it actually makes sense. Basically, the idea behind the n log n version is actually binary search on the length instead of the index. And basically, the idea here is that, okay, you know, let's actually, you know, erase all this a little bit. And then the idea is, actually, this is 0, maybe. No, this is, what am I doing? No, this isn't right. What we want to store is the envelope, right? So, I guess we could just do this. Yeah. I think. But yeah, but now best actually stores a different thing, right? It is, it will store the envelope that, the smallest envelope that that has a sequence of the smallest envelope that's a, that, how do they phrase it? That is a streak, maybe, that has a, that contains I envelopes, right? And why does this work? And the reason why this works is that it's greedy. Basically, okay, right? Let's say, you know, I'm just throwing random numbers. I'm not going over a test case for now. But let's say, you know, you have a best of 2, which means the smallest envelope that can have 2 envelopes, including itself, right? So let's say for explanation, let's just say this is like 10 and 12, right? Well, the short answer is that, okay, everything that comes afterwards because we sorted, everything that comes afterwards will be bigger than this number, right? In terms of in one of the two dimensions. And the part that I think I was a little bit unsure about is that, which is why I didn't do it earlier, was that I thought that there might be a sequence where, like, okay, this could be a sequence, this could be a sequence, this could be a sequence, and so forth, right? Like, how do you choose between them? And then the answer is actually that because we do them in order, because we sort the envelopes already, this order will actually be the other way around, right? It'll be 100, let's say 299, 398, and so forth, right? And then the key part about this sort, which I actually didn't realize, I always sort, but I forgot about this invariant that happens, is that your next number, it's going to be, let's just say this is some x, this is some y, or w and h, because that's in the problem. The next number will always be some h sub I, where w sub I is always going to be bigger or equal to w sub I will always be bigger than equal to w, because this is what we sorted on, right? So then hi, so the only thing that we have to ask ourselves is hi greater than, well, has to be greater than, but just for clarity, is h sub I greater than h? And because of this, that this is always going to be true no matter what. We only have to then we want to minimize this, because even if w is the biggest number, it doesn't matter what it is, even if it's the biggest number, it's always going to be equal to or smaller than this, right? So then therefore we want to greedily minimize this number. And also the other thing to note is that we can split this up a little bit. If this is bigger, there's two cases. One is if this is bigger than w, then this case can happen. If w is equal to w sub I is equal to w, then hi is always greater than h, right? So if this is the case, then we can ignore it, because this is not going to improve your situation. But because of that, we can assume that we ignore the other case, or this case doesn't matter. Then this case, we always want to minimize the h for a given length. So that's basically the idea. Because if you can extend the length, obviously you would just extend it to the best of 3. So let's say we add a 100, 100, or 101, 101, that would be in best of 3, while we still keep, say, 3 sub, or w sub h here maybe. And then here we can say w sub 1, h plus 1, and so forth, right? And then here, the beautiful part about this now, of course, is that if you look at this sequence of best going from best of 0 to best of 1, best of 3, say this is going to be, say, none or 0 0 maybe. I don't know how I want to do it. Let's just say 0 0. Yeah. Yeah. And then best of 1 is equal to some other number, right? So some number. You can see that in this case, well, actually, I guess, can w be the same? I guess w technically could be the same, but in either case, it doesn't matter, because if w is the same as we said, h is going to be smaller, right? And yeah, it does. And in this case, you can see that this is an increasing sequence. So, and that means that you can do a binary search. And because you can do binary search, this is going to be n log n. So that's basically the idea about it. You try to find the point in which this to insert it. because let's say a number that comes later, let's say this is 1, this is 8, I don't know, this is just random number 2, this is 7 maybe? Would that happen? No, so this cannot happen actually, because that means that I was just thinking about whether that could happen, and actually the answer is not, because if this can happen, that means that there exists at least a 1/6, right? That's just like by definition, because otherwise you cannot extend the 1 to a 2. So then this is say 3/8, right? And then now let's extend this a little bit so I could have more room. Let's say this, right? And then now let's say we have a number that's 4/8. Well, you do a binary search, and then it goes to here, where 4/8 is bigger than the last number that could be bigger than is 2/7, and because of that, then now we could, in theory, that means that if you add 4/8 to 2/7, there's a sequence of length 3. And if there's a sequence of length 3, then we just check whether we, do we use... Also, this is impossible. I messed up a little bit here. Let's just call it 310. But yeah, in this case, we will update this to 4/8 to minimize the height. So that's basically the idea, because we know that now there's a best answer with the length 3, but now we want the h to be as small as possible for future purposes. As we know, because now you can break it down to 2 cases, right, or a couple of cases for this case. Let's say you have 310 and here, and we have to choose between these two. There are only a couple of cases to consider, which is why we're able to do greedy. And sometimes the proof will be just doing every example, right? And then here, for example, you have 4/9, which is, let's say this is a big case. Well, 4/9 is not going to fit in here anyway, so it doesn't matter. But let's say we have 4/11. Well, 4/11 does fit into 310. Oh, actually, in this case, I think I messed up. I think what we want is actually for the tiebreaker. I think this is why I got a little confused. We want actually the bigger numbers first, so that here we will have 11. We want bigger numbers on the right side, so that when we go, let's say later we get a 4/8, we can connect. We could figure out where to connect to, right? And let's actually pick a bigger number so so now let's say, there are only a couple of cases now. Okay, now it makes sense. Sorry about that. Sometimes these things are hard, and that's why you have to explore them. And as I say, I am solving this live. I don't, obviously if I'm reading off an answer, this would be much easier. But yeah. So now, now all the numbers will have to be smaller than 15. So let's just say this is 12, right? 12. Well, this number is going to be bigger than this number, so obviously now you update this to 12. And then the other case is such that, that's one of the cases, and this can only go down, so this applies. And then the only other case is if this is a 5, and, well, this is not the only other case, but 18, right? Well, in this case, obviously, you just extend for 15, so you wouldn't consider the 310 anyway. Like, it's the same thing, because, you extend this anyway, right? Let's say this is 5/12. Well, if this is 5/12, if this is 5/12, then you cannot extend this to 4/15. So you would update this to 5/12, right? Because you cannot extend 4/15 anyway. So then on the last number, Did I mess up somewhere? Dong dong dong. Because then you, if you keep 310, if you keep 310, then you can extend it. But if you keep 415, you cannot. Did I mess this up? Dong dong dong. Okay, let me try again. So if this is a bigger number than this, then you can do, you know, it doesn't matter which one you keep. If this is in between, oh, that's because I messed up again. Okay, I see. Because this would also never happen. Because in this case, I think I am just being dumb today. At least with the explanation. But at least I'm working it out so that you can see where I'm making the mistakes. This could never happen. Because if this is the case, if we have a 415, you know, you would just have a 415 here, right? So that means that by definition, or at least going through the examples, let's say we have a 4.8, right? And we want to make an argument that we want to update this to 4.8 because there are a couple of scenarios. Well, if later we get 4.5, say, if we get 4.5, well, we obviously want to update this anyways, and it doesn't extend 310 by definition, and it goes all the way down. And then now if we have a bigger W, and you know, this could be something big. Well, in this case, it does, you know, it's bigger than either one. So then what happens if this is 5.9? Well, if you have a 5.9, or even 510, I guess, because of tie breaking, in this case, this number will fit into the 4.8, but not the 310. So, or the other way around, 310 will fit into the 510, but or 310 will not fit into the 510, but the 4.8 will fit into the 510. So as a result of that, it's always optimal to choose 4.8. Okay. I keep on confusing myself the invariant. I apologize for that, but like I said, this is me explaining this live, and you know, but that's the idea behind this problem. And now from all this foundation, now you can write the code, right? So here we have for trying to think. Yeah, for an envelopes, let's say index is equal to, and we're going to use, I'm going to use the in Python the bisect library. You can do your own thing, of course. Yeah. I'm just trying to think about the off by ones in this case. But basically, this is the insertion point in which, so yeah. So basically, we're using binary search library. Feel free to practice, you want to upsolve it, practice your binary search. Feel free to do that at home as well. So now if index is equal to the length of best, this means that we have to add it at the very end. Then best we append WH. Otherwise, best of index is equal to WH. Oops. And then at the very end, we just return the length of best minus 1. I think that should be good enough. And then now let's run the code real quick. This is a very long video. But okay, did I miss something? Oh, whoops. I forget to actually put in the best. That's where we're binary search on, of course. Cool. This is not the right answer at all. Do I have a type? Maybe this is bisect, right? Let's see. I thought it was bisect left. Let me read this real quick. I'm gonna just try this a little bit YOLO, but I thought it should be bisect left. Guess it didn't matter. What am I doing wrong here? Let's see. I'm tempted to just print this, but it may be a long print. Yeah, let's just do it. If it complains, it complains. So yeah, so here it goes 0, 0, 2 is the best. That's not right. Does that return? So the insertion point is here. Oh, I messed up a little bit. I have to do some checks on the height. Dong dong dong. I mean, that's why it is wrong. But I'm trying to. So what I'm thinking right now is whether I need the W at all, because the W is known to be, it's going to be strictly increasing. So then we can just update just this part. But we can also do the other way, I think, of if let's see. Okay. Best of index -1 sub 0 is greater than Yeah, I mean, basically we want to do what we said earlier, which is that we want this to be the min. So if the width is no, this cannot be true, obviously. Okay, so we just compare the height, right? Height, then so my one, you go to continue maybe. Still a little wrong, or maybe a lot wrong. Okay, so 2, 5, we got 3, That's not right either. Because clearly, you know, that violates our invariant. I think we don't need the, now that I think about it a little bit, I don't think we need the W because it is assumed that yeah, I don't think we need the W because it is assumed that everything in before will have a smaller W. So I think that just messes up my binary search. What I want to do is binary search on only the 422, which is kind of what I did with this little hack. So I think I need to clean that up a little bit. Can binary search have a key? Let me see. On binary. Stance is no. I think we can just do the height, the width, sorry. So we can do something like this. Because I think that's basically what, because all the numbers afterwards will have, and if it's equal, and if it's equal, you want the later one anyway. So yeah, okay, yeah. That's a way. I have to think about that one. But yeah, let's give it a submit. Hopefully this is fast enough. Cool. Yeah, so this one is a very tricky one. I think historically I always have I mean, I don't have trouble with this part, but as you can see, there's a lot of observations and proofs and just like understanding that goes into it, right? I mean, this is a very like short 5 lines of code or whatever it is. But I've always struggled a little bit to make sure that we find that tonic city, especially like just ignoring with but going over the complexity, obviously this is going to be O of n for the number of loops, and this one's going to be O of log n at the worst, or log best if you want to call it that. So in total it's going to be O of n log n time. And in terms of space, it's going to be O of linear space. That's all I have for this problem. It's very tricky. Let me know what you think in the comments. Maybe I need to explain this a little bit better, but it is a long video, so let me know what you think. But at least you saw both ways of doing the longest increasing subsequence progression. Hope that's helpful. But yeah, Anyway, that's all I have, I guess. What a problem to almost finish off the month. Let me know what you think. I'll see y'all tomorrow. Have a good day. Have a good rest of the week. Stay good, stay healthy, stay well. I'll see y'all tomorrow. Bye-bye.